In this lecture, we introduced summation notation, which is a convenient way to write sums with many terms more compactly. We will use this notation later when approximating areas and distances. A standard way of writing sums in compact form uses the capital Greek letter sigma. If am plus 1, and so on an are real numbers, and m and n are integers, such that m is less than or equal to n, then the sum of these numbers is denoted by sigma from I equals m to n of ai. The letter sigma stands for the sum, and the notation sigma from I equals m to n tells us to start the summation at I equals m and end it at I equals n. Here I takes on consecutive integer values, beginning with m and ending with n. The letter I is called the index of summation. Any other letter can be used instead as the index of the summation. ai is usually an expression depending on I, which is called the general term of summation. As an example, consider sum from I equals 1 to 5 of I. We start with I equals 1, so we plug 1 for I to obtain the first term of the summation, 1. The next value of the index I is 2. Again, we plug in 2 for I and obtain the next term of the summation, 2. We keep going in this fashion, getting 3 plus 4 plus 5. Here we stop, since 5 is the last value of the index. The sum of numbers 1, 2, 3, 4, and 5 equals 15. Thus we computed the value of the sum of I from I equals 1 to 5 to be 15. The next example is the sum from j equals 4 to 6 of j squared. We start with j equals 4. Substituting number 4 for j, we get the first term of the summation, 4 squared. The next value for j is 5, and substituting it in, we get 5 squared. The next and the last value for j is 6. Therefore, the last term of the summation is 6 squared. Now we just square and add these numbers. 16 plus 25 plus 36 equals 77. So the value of this sum is 77. The next example is the sum for k equals 2 to 8 of 1 over k. This means we need to sum up all the fractions with numerator 1 and denominators ranging from 2 to 8. We get 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. The least common denominator here is 8 times 7 times 5 times 3, which is 840, and the sum equals 1443 divided by 840. The next example is to compute the sum from I equals 1 to 7 of 2. As before, we start with the index I equals 1 and obtain 2 as the first term of the sum. Then we set I equals 2 and again get 2. In fact, we get 2 as a term of the summation for every value of I. So we need to add 2 7 times, which gives us 7 times 2 equals 14. Now let's look at the opposite question. Write in sigma notation the sum square root of 3 plus square root of 4 plus square root of 5 plus square root of 6 plus square root of 7 plus square root of 8 plus square root of 9. We see that the general term can be expressed as square root of I. Then we need to start the sum at I equals 3 and end it at I equals 9. We also can write the general term as square root of j plus 2. In this case, we start our summation at j equals 1 and end it at j equals 7. There are many other ways of expressing this sum in sigma notation. The next example is the sum from I equals 1 to n of 1. Here n is any natural number greater than or equal to 1. The general term of this summation, 1, does not depend on I. Therefore, we just need to add 1 for each value of I from 1 to n. We add 1 n times and obtain n. The next example is to evaluate the sum from I equals 1 to n of I. This means we need to sum up all numbers from 1 to n. The general term of this summation depends on I, so we cannot simply multiply it by the number of terms, as in the previous example. To find the value of this summation, we will use the same method as the famous German mathematician Carl Gauss did in the 18th century. He was 10 years old at the time. The story is presented as follows. One day, the teacher of Gauss gave the class an assignment to keep them busy so that he could take a nap in the back of the class. Students were told to add all the whole numbers from 1 to 100. That is 1 plus 2 plus 3 plus 4 and so on, plus 97 plus 98 plus 99 plus 100. Let's try. 1 plus 2, 3, plus 3, 6, plus 4, 10. Well, it is going to take a while. This problem would require students to perform 99 additions to solve. Therefore, the teacher calculated his students would be occupied for at least an hour. To the teacher's surprise and annoyance, Gauss brought him the correct answer after only a few minutes. Here's how young Gauss arrived at his answer so quickly. Instead of adding numbers in sequence, he first added 1 and 100 and got 101. Then he added 2 and 99 and again got 101. He added 3 and 98 and once more got 101. Gauss observed that the sum of pairs of numbers from each end working in toward the middle is the same value, 101. Since there are 50 pairs of numbers, the sum of all numbers would be 101 times 50 equals 5050. There is nothing special about the number 100 here. Let's use the same trick to find the sum of numbers up to n. We see that 1 plus n equals n plus 1. 2 plus n minus 1 again equals n plus 1. 3 plus n minus 2 once more equals n plus 1, and so on. We have n over 2 pairs, each of which has sum n plus 1. Therefore, the answer is n over 2 times n plus 1. I assumed that n is even here to get the number of pairs n over 2. However, it just takes a moment of thought to convince oneself that the same formula is valid for an odd n. So far, we obtained two summation formulas. The sum of 1 from I equals 1 to n equals n, and the sum of I from I equals 1 to n equals n times n plus 1 divided by 2. There is also a formula for the sum of the squares of the first n positive integers. The sum of I squared from I equals 1 to n equals n times n plus 1 times 2n plus 1 divided by 6. And the formula for the sum of the cubes. The sum of I cube from I equals 1 to n equals n times n plus 1 divided by 2 squared. These formulas could be proven using the principle of mathematical induction. Formulas for the sums of the powers of positive integers were discovered by a Swiss mathematician, Jacob Bernoulli, at the end of 17th century. To manipulate summations, we use the following rules. The sum from I equals m to n of c times ai equals c times the sum from I equals m to n of ai, where c is a constant, meaning that it does not depend on I. This rule tells us that we can factor out constants from the summations. The sum I equals m to n of ai plus or minus bi can be written as the sum from I equals m to n of ai plus or minus the sum from I equals m to n of bi. These rules are consequences of the usual commutative, associative, and distributive laws of addition. We will use these rules together with the summation formulas to evaluate sums. For example, find the value of the sum from I equals 1 to n of 7 minus 5i. First, we split the sum into two parts. The sum of 7 minus the sum of 5i from I equals 1 to n. Now we factor out constants 7 and 5 from the summations. We obtain 7 times the sum of 1 minus 5 times the sum of I from I equals 1 to n. Now it is time to use the summation formulas. The sum of 1's equals n, and the sum of I equals n times n plus 1 divided by 2. Therefore, we get 7 times n minus 5 times n plus 1 divided by 2. We simplify this expression by finding the common denominator and arrive at the answer, 9n minus 5n squared divided by 2. The next example is to find the value of the sum from I equals 1 to n of 3 plus I squared. First we expand 3 plus I squared and get 9 plus 6I plus I squared. We distribute the sum to each of the 3 terms of this polynomial and factor out constants. We obtain 9 times the sum of 1 plus 6 times the sum of I plus sum of I squared, where I runs from 1 to n. Now let's use the appropriate summation formulas for each sum. The sum of 1 from 1 to n equals n. Therefore, we get 9 times n plus 6 times the sum of I, which is 6 times n plus 1 over 2, plus the sum of I squared from I equals 1 to n, which is n times n plus 1 times 2n plus 1 over 6. Our last example is to find the value of the sum from I equals 1 to n of I cubed minus I. Again, we distribute the sum to each term and get the sum of I cubed minus the sum of I for I equals 1 to n. We apply formulas for the sum of I cubed and the sum of I, and obtain the answer n times n plus 1 over 2 squared minus n times n plus 1 over 2. This is the end of our lecture.